today. So 1.2 memory and storage. So this is the list. Good, I'm glad, and well done for being here, Rom. It's very impressive. We have got 12 people here currently. Most of you are hiding. Just say hello. I mean, it can't be that bad. Is the volume okay? Is it too loud? Can you hear me? Let me know if you've got a problem with the volume. I'm using a different mic today, which I think is slightly better. So we need to look at units of storage, and that's bits, bytes, nibbles, all of that malarkey, and then working between the two of them, or between different units, converting from denary to binary, adding binary numbers, denary to hex, binary to hex. Hello, Warren. Nice to see you. Thank you for being here, dear man. If indeed you are, or whatever, it doesn't matter. But thanks for being here. Calculating size of text files, which is a piece of cake, and actually very logical when you think about it. And I reckon they might put that in the exam this time. They didn't do anything in the last exam on that. Binary code and characters, character sets, and then Unicode and ASCII. So it is quite a lot to cover, but actually, given that most of your maths is pretty good, I think it'll be fine, because the binary and hex stuff is actually, it doesn't require much maths at all. So 20 minutes teaching, I think, is a bit hopeful, but it's 8:06. So let's see how we go. Right, starters. Why do computers use binary? They love this at the start of an exam. So we've got 18 on now. Do say hello. Why do computers use binary? So if they give 1 mark for it, you can say that, in fact, it's usually 2. So they'll say that computers are made of or consist of circuits. And these circuit boards have got 2 states. They've got on and they've got off. And that's easily represented in binary, because binary, 1 is on and 0 is off. So 1 is true and 0 is false. Easy peasy. You can pick up 2 or 3 marks at the start of the exam, but you've got to make sure your wording is quite similar to that. Why do computers use binary? And several of these topics are dedicated to just understanding that computers use binary. So how's an image put together in binary? How's a sound put together in binary? And so on, okay? and then characters as well. Okay, so 1 off, 1 true, and 0 false. That is how that all works. Okay, let's push on. So we're now going to look at units of data storage capacity, which is a fancy way for saying all of this stuff, which I know you're probably aware of. So just to break this down, they could make you do some calculations, but the hardest bit is surely these top 3, because they go in 4s and 8s. So the smallest unit of data storage capacity is the bit. This guy, let's go back to here. This guy, get off. This guy here, this is your bit just here. And a bit is either on or off. It's only got 2 states, true or false, okay? Then we've got the nibble over here, which is 4 bits. So it's 4 of these bits. And then you've got a byte, which is 8 bits. So as long as you can remember bit, nibble, byte, the rest of it is plain sailing. Because if you notice that once we get down to here, to kilobytes, gigabytes, terabytes, and all that malarkey, it's just 1,000. So you're going up by 1,000 each time. So there are 1,000 kilobytes in a megabyte, 1,000 megabytes in a gigabyte, 1,000 terabytes in a petabyte. So it's pretty straightforward stuff. So they can give you something in bits and make you work it out in kilobytes, or give you something in megabytes and make you work it out in bits. So the most sort of difficult thing you'll have to do is to navigate the 8s down here for the bytes, okay? That'll be the most tricky thing you'll have to do. But as long as you remember that a bit is 0 or 1, a nibble is 4 bits, and a byte is 8 bits, it's plain sailing. It really is, okay? We've got 18 people, so do say hello in the comments, please. Right, let's push on. Right, so let's jump into conversion. Dead easy. But to just state the obvious for you, binary's got 2 states, it's 0 or 1. Denary, which we count in all the time, decimal denary, it goes from 0 to 9. And you're thinking, but hang on, what about 10? Well, actually, you go to 9, and then you've got your 1, which is your 110, and you go back to 0. Bear that in mind when we talk about hex, because hex is actually just dealing with 16s rather than 10s. It's quite easy. So let's have a look down here at hex, which works this way. We've got A is 10, B is 11, C is 12, D is 13, E 14, and F 15. There ain't no G. it's tempting to have a G because you think, well, it's 16, but actually it then goes to 1, 0, and that 1 is the 116 when it ticks over, just like we've got 1, 0 in decimal, which is 110 and no units. We sort of do it all the time, but we're so used to the denary, the decimal system, that we tend to ignore everything else. Okay, so let's look at how you convert things in binary, from binary. It's tempting, if your maths is good, to simply do it inside your head and write down the answer. My advice to you is to actually draw this grid each time. It might seem painful, but it's very, very easy to make a simple slip up when you do this, and that's suddenly 1 or 2 marks lost. So in this instance, we're going to take this binary number, and you know it's binary because they've got this little 2 down here. That means that it's binary, okay? So we've got our binary number here, and we're going to convert it into decimal, into denary. Number 1, draw the grid. The hardest thing to remember is that the grid it goes from right to left. It's a bit like writing in Arabic. You go from right to the left-hand side of the page, and you start from 1, and then you double. Now, you're only going to have to do 8 bits. So that's 1 bit, that's 2 bits, that's 3, that's 4, that's 5, that's 6, that's 7, and that is 8. So you're only going to have to do an 8-bit number, all right? And 128 takes you to 8 bits. So you're never going to have to do more than that, which means the maths is actually not going to be too terrifying. Right, let's push on. So you've drawn your grid, okay? The next thing is you drop the numbers into the grid. So do you remember, I'll go back a step. The number we were converting is this one here. Oops, the number we were converting was this one here. 10101010. Happy? So all you've got to do is drop that one into the grid. 10101010. Okay? That's it. If you've done this so far correctly, you've probably eliminated any chance of messing up. We've got 19 people now. Do say hello. So let's have a look. So we've dropped the numbers into the grid. The next stage you need to worry about is to do some simple maths. So all you do is you read from the bottom of our grid, and you look at where we've got ones, okay? Because those are the ones we're going to be concerned about. That's a 1, that's a 1, that's a 1, and that's a 1. We can forget these zeros, right? They're not important to us. These zeros, we don't care about those for the time being. That's me scribbling it out really badly, okay? So we're not too fussed about these. We're going to focus on the ones, and we do some simple math. So we go to where there's a 1 on the left-hand side, or the right, makes no difference. And we say, okay, it's 128. And we're going to add 128 to the next one that's got a 1, which is this one here, 32. Quick maths tells us that 128 plus 32, well, 128 plus 2 is 130. 130 plus 30 is 160. Quick maths, quick maths. Then we're going to add the 8 to it, because that's the next one that's got a 1. And then we're going to add the 2 to it. Any of you geniuses want to tell me what this answer will be? To answer your question, live stream about another half an hour. And I've got some quizzing at the end, which you don't need to stick around for if you don't want to. But I reckon half an hour. I'm going through it at breakneck speed, okay? Dan's come back with 170. Do you know what, Dan? You're absolutely spot on. But even if you didn't get to the answer, the maths is actually quite straightforward. 128 plus 32 plus 8 plus 2. Can I use a calculator? No, because the maths you've got to do, it's not that hard. And of course, you can write it out on paper and work out an addition if you want to, but it's quite straightforward. Okay, so that is your converting that way. Now let's go back the other way, and we're going to convert this number. So that was from binary to denary, and we're now going to go from denary to binary, from decimal to binary. So in this case, we're going to convert this, and we know that this number is a decimal number because you've got base 10 written down here, okay? Okay, this is slightly different, but you do the same principle again. You draw the grid. You start from 1, and you double it until you get to 128. Easy peasy. You'll recognise these from phone memory, 16, 32, 64, 128. When you buy phone memory, guess what? It's in binary, so that's why you have those numbers there. Good. So let's crack on. The first thing we ask ourselves, don't forget, what we're looking to do is to convert this number 170, got 22 on, we're going to convert 170 into a binary number. So you ask yourself this question over and over again. What's the largest grid number? And by grid number, I mean the numbers on this grid here. So what's the largest number on this grid that goes once into our number? Well, guess what? It's 128. So guess what you do? You work out that it's 128, and then you go on and you write a 1. Now, this is where you need to do some maths. So 128 goes into 170 once, and you need to work out the remainder. Well, the remainder is 42. 128 plus 2 is 130, and 130 plus 40 is 170. So you end up with the remainder. And notice I've used the word modulus down here. So if you look at the specification, that's one of the codes that you need to understand. It was in the mock this year. Mod is remainder, okay? I'll come on to that later on, but don't worry about it now. But mod is the same as remainder, okay? So we've got a mod of 42. And then guess what? You ask yourself exactly the same question again. What is the biggest grid number that goes into 42 once? Well, it is 32. What's the remainder? The remainder down here is 10. And guess what? We ask ourselves exactly the same question again. So let's do that. So 8 goes into 10 once with a remainder of 2. So you're obviously on the next one going to put a 1 there. And I'm sure you're ahead of me, but all you do now, because we've now dispensed with the number, there's nothing left. We've got a modulus of 2. There's no remainders now. So we have dealt with our number. We've been through the entire thing, and now all we need to do is fill in the rest of the gaps with zeros, like so. Oop, I didn't. There we go, like so. Okay. Simply fill out the remainder with zeros. So the whole number's done, and that's how you convert a decimal number, a denary number, into binary. I know I'm talking quickly. I hope that makes sense. All right, so now we go on, hexadecimal. So hexadecimal takes us up to 16. I would like you to cast your eyes on this particular diagram. And I'll give you a challenge while we're here, is that if you spend 3 minutes looking at these binary numbers, it might take you 4, but if you spend 3 minutes, Google it when we finish this, and spend about 3 minutes looking at binary numbers from 0 to 20, and you will suddenly go, oh, I see. You'll suddenly work out how to count in binary. And if you can do it, it makes life remarkably simple, because it means you understand everything that you're doing. 0, 1, 1, 0. Something to point out to you just to get you started is that if you look, let's go over to here. If you look over here, 1, 0, 1, 0. It just keeps changing on the right-hand side each time, and it fills out from right to left, okay? And the number obviously gets longer and longer and longer. Okay, and then we've got hexadecimal over here, which when we get to 9, 10 is A, and then you've got A, B, C, D, E, F, G down here, okay? So that's the key takeaway there. Okay, I am back. So let's go forward to this. When you do your hex conversion, you've got to go from denary to binary and then from binary to hex. So you've actually done most of this anyway. So we'll deal with a bit that you need to know, all right? And I mean, obviously, because you're working with 16s, you can probably work it out in your head. I would advise you to do it this way, but if you do work it out in your head, double check it, okay? These questions are generally worth a couple of marks, but when you put them all together, it could be 6 marks, which is close to that sort of a grade boundary. So it's worth really taking your time. So let's look at this problem. You are taking the hexadecimal number 5F, and you're converting it into, we've got 23 on, do say hello. We are taking the number 5F, which is hexadecimal, and we're turning it into a denary number. So the first thing we've got to do is turn it into a binary number. And to do that, you create 2 nibble tables. Now, a nibble table is a table for each of these numbers, a table for the 5 and a table for the F. Those of you who are more advanced will realise that you can do this in your head, that the 5 refers to 5 times 16, and as long as you know what F is, A, 10, B, 11, C, 12, and so on, you can work out what it is inside your head. If you get there before me, put the answer in, okay? But you do exactly the same. So with 5, let's do our nibble table. What's the biggest number in our grid that goes into 5 once? It's 4. What's left over? It's 1. So that's that one done. Then F we know is 15. 15, 8 goes into 15 once, leaves 7, which means we've then got the next number, which is 4, and then the next number is 2, the next number is 1, because 8 and 4 is 12, and 2 is 14, 1's 15. So if you go through exactly the same thing that we did, you then end up with this binary number. What you have to do once you've done that is to smash these binary numbers together, to smash those two nibble tables together, and then you can work it out exactly as you did before. Notice how, by smashing them in, you go back to having it as 8 bits, 1, 2, 4, 8, 16, 32, 64, 1, 2, 8. So you go back to that, and then you do some simple maths. 64 plus 16, 64, 74, and 6 is 80, 88. Are we there ahead of me? What do we think? What is the final answer? I know you lot are super good at this. What is the final answer? Any idea? Any ideas on what this could be? Oh. Anyway, your maths is more than good enough to master these. 95, says Dan. Let's see if he's absolutely spot on. Let's see if Dan is correct. And yes, he is. Well done. Outstanding. You are a superstar. So let's go on to the next bit. Get rid of that and go on to our next slide. So that's just to recap the fact that if you're going from hex to decimal, you go through binary. 2 nibble tables and you're done. Smash them together and the job's good. Binary addition. I like it when things are easy. I mean, this binary, honestly, there could be a whole grade in this. It's so straightforward. Binary addition. There are a couple of things you need to remember, right? And they are, if you look on the left-hand side of this, 0 plus 0 is 0. Don't need to be Einstein to work that one out. 0 plus 1 is 1. So far, so good. 1 plus 0 is 1. Not difficult. This is year 2. But then things get a bit binary-ish. 1 plus 1 is 1, 0. And 1 plus 1 plus 1 is 1, 1. Okay? Again, if you learn to count in binary, this makes absolute sense. It just makes complete sense because that is how this number system works. So let's look at this binary addition on the right-hand side here. I will whiz through it nice and quickly. We're going to add together these two numbers, okay? 1101, 1010 with 10100, 1010. So let's go through it one line at a time. We start from the right, and this one is nice and easy. 0 plus 0 is, guess what? It's 0. 1 plus 1. Ooh, hang on. 1 plus 1. Let's have a look at our cheat sheet. 1 plus 1 is 1, 0. Okay, so in that case, you do. Let me get rid of that. Get off. 1 plus 1 is 1, 0. So we do 0 down and carry the 1. Okay, 0 plus 0 is 0, plus the 1 we've carried is 1. So far, so good. 1 plus 1 is, let's cheat, 1 plus 1 is 1, 0. So we do 0 down, boom, 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 0 down, carry the 1. Okay, 1 plus 0 is 1, but 1 plus 1 is 1, 0. 0 down, carry the 1. 0 plus 0 is 0, plus 1 down here is 1. We're getting through this now. 1 plus 1 is, let's cheat again, 1 plus 1 is 1, 0. This is quite repetitive, isn't it? 1 plus 1 is 1, 0. 0 down, carry the 1. And 1 plus 0 is 1, but 1 plus 1 is 1, 0. 0 down, carry the 1. And there it is. Boom. Easy peasy. Easy peasy, isn't it? So it might be worth going back and having a look at that. But literally, the mantra you've got to have in your mantra you've got to have in your head, as hard as it gets, are these two here. And to be honest, they rarely get you to do 1 plus 1 plus 1, but you should know it. The most tricky thing they often do is just to get you to find out what 1 plus 1 is. And it's 1, 0. And you put a 0 in the answer and you carry the 1. Okay? Do you know what it's exactly like doing Denary calculations? Ah, Abra, good day, man. How are you? Nice to see you. What a good fellow. So this is the binary addition. This is how you do that. It's easy peasy. I'll make this available to you so you can use it, but I imagine that most of you are pretty happy with that. Excellent. Right, next. Binary shifts. You're probably less happy with this, although the principle is actually quite straightforward. And I think maybe what people miss a lot with the binary shifts is what they actually do. binary shifts are designed to multiply and divide binary numbers. And you can either shift left or shift right. If you shift right, you divide. If you shift left, you multiply. I use a little mnemonic. I think of a king standing there, and he might say, or she might say, the queen might say, it is my right to divide. So it's my right to divide. The crown, all of that works well for me. It's my right to divide the people. Okay, so right to divide, that works for me. You go right to divide, you go left to multiply. That's the only thing you can mess up with this. Okay, some other principles around binary shifts are this, that you do it in steps of 2, 4, 6, 8, 16, 32, 64. You will notice, come back, you will notice that these double each time. So 4 is twice 2. I mean, this is binary all over, isn't it? 8 is twice 4, 16 is twice 8, 32 is twice 16, and 64 is double 32. So it simply doubles each time. So if you're multiplying, and think about it, if you're multiplying, you're going left. If you're dividing, you're going right. So if you're multiplying, you're doubling the number. And if you're dividing, you're halving the number each time. Okay. Now they talk about places or they talk about bits. So this could be one place or one bit. So if you go one place or one bit, you divide and multiply by... Wrong way. If you go one place or one bit, you multiply or divide by 2. If you go 2 places, you divide and multiply by 4. It's quite tempting to get this wrong. But if you think about it, it's doubling each time, just like your bit table, okay? It's doubling each time. So they ask you the question, what would the impact be if you did a two-place shift or a two-bit shift to the left or right? And then you would talk about it. So two places means that you're dividing it by 4, okay? 3 places, dividing and multiplying it by 8. So that's the only bit that's a little bit difficult to get your head around. Other than that, it's really quite straightforward. Okay. Okay, so let's talk about left shift now. So left shift means shifting all the digits to the left. So if I start over here, let's go to here and look at this one. So this is the binary number, and in the exam they will say, take this 4-bit number, and 4 bits, because it's got 4 digits, 8 bits, 8 digits. They don't do anything for you more than 8 bits, 8 digits in binary. So if they said you do a left shift, 1 bit to the left, a binary shift 1 bit to the left, all you do is that you move everything to the left and you add a 0 here, okay? And that will double the value. I've done the Denary equivalent here. So this is 12. 1100 is 12. If you double it, it becomes 11000, and in Denary it would be 24. If you go 2 places, so this is the number, we've doubled it. From this number, this is double. See, 24 becomes 48, 48 becomes 96. I thought I'd put this in there so it's more clear. But you can see each time that's adding 2 zeros, 3 places, 3 zeros, 4 places, 4 zeros. Couldn't be easier, okay? So binary shifts left are dead easy, okay? Left is multiplying. So you shift all the digits along to the left, the required number of places, and then add the required number of zeros to the right-hand side. Easy peasy. It's not hard maths, that. Well, it's not even maths at all, really. Well, I suppose it is, but it's just so simple. Okay, let's go on to the next one. Now we're doing a binary shift right, and there's one more thing to bear in mind here, which is this. The same principle applies, that you're actually going to lose, you're going to take a number away. So in a right shift, and it's right to divide, and bear in mind we're doing binary here, not denary. So you can't have decimals. You can't have 0.5 or 0.3. It's whole numbers only. So you shift all digits along to the right, the required number of places, and numbers that drop off the end are discarded. So this time I'm starting over here, right? So we're starting with the denary number 36, which is 100100. So if we do a 1-bit shift to the right, or a 1-place binary shift to the right, we literally lose a number. So we've lost this one here. So it becomes 1010. If we go 2 places, we go from 36 to 18 to 9. It's halving each time. And in that case, it just becomes 1001, which is this part of the number here. So again, we're losing that 0, all right? Now, look at this. This is where I reckon they might ask you a question about this in the exam. Look at what happens here. If we go to 3 places, see how this 9, if you halve it, you end up with 4, because in binary you can't have 0.5. So when you do that, you actually lose accuracy, okay? Or precision, they call it in some examples, but accuracy, which means that this should be 4.5, but in fact it's not, it's just 4, okay? Because it's in binary. So therefore, you lose precision as you complete more and more shifts right. And if you go one more shift right, you end up with 1, 0. So sometimes, and they've asked this question before, what would be the impact of doing a right shift? They'll give you a number and say, what would be the impact of doing a right shift 2 places? And that doesn't mean you give the answer and tell them the number would be 10, 10, 10. It means that you would say, if you're going 2 places to the right, 1, 2 places, it means the number would be divided by 4, because it's divided by 2, divided by 4, divided by 8, divided by 16 with each place, okay? That's the first thing. And then you'd say there'd be a loss of accuracy. You've done a few 2 markers on that. So I hope that makes sense, this idea of a loss of accuracy. How are we doing? 31. We're doing really well, actually. This is kind of just to repeat what I've said before, which is that right shift is division, left shift is multiplication, and that's how it works, okay? So have a look in the blue CGP books, have a look at your notes, make sure you're happy with that. But all of this binary stuff, you can absolutely predict what they're going to do. Just make sure that you read the question, and if it's, because it's either going to ask for you to do some conversion and do some maths, or it's going to ask you what the impact would be, which means describing what would happen to the number. It's divided by 4 and it will lose accuracy. It's multiplied by 6, etc. Okay, so that's what you need to do. Right to divide, okay, left to multiply. That's what you need to know. Good. I hope that makes sense. Right, let's go on to this one. Characters. We're whizzing through this, actually. 32. This is literally about 3 months teaching we just done here in half an hour. So this is the first part of characters, images and sound. And I thought I'd deal with characters straight away because it's just so straightforward. Right. Imagine you're sat there and they will say, what is a character set? Do not start talking about Unicode and ASCII. That's not what they want. If they say, what is a character set, your magic phrase to get yourself 1 mark or even 2 is to say, it is all the characters. No, sorry, I made the same mistake myself. It is a set of characters the computer can understand. So that answers the question, what is a character set? It's a set of characters the computer can understand. This question has appeared again and again and again because they can only ask so much. So this is your opening gambit, 1 mark. What is a character set? It's a set of characters the computer can understand. 1 mark. Right. Then they'll look at the 2 different character sets. You've got ASCII, which is 8-bit, and you've got Unicode, which is 32-bit. Well, clearly, Unicode being 32-bit represents far more characters than ASCII. Yes, I have done that, but I can go back and do the hex again, Abra. That's not a problem. I can go back and do that at the end, okay? It's 2 nibble tables. It's as simple as that. The last time I did this presentation, I talked about nipples all the way through, which didn't help, so it's 2 nibble tables. So ASCII and Unicode, one is 8-bit and one is 32-bit. So it is clear that with ASCII, an 8-bit number, if you have 8-bit, so 8 characters in binary, 1111, 1111, the Denary equivalent is 256. So it's like there are 256 slots. If you think about you mucking around in Paint or in Photoshop, and you look at an 8-bit color, you've got 256 color variations. So ASCII is a smaller character set in terms of size, but it can only represent 256 characters. And then they'll say, what is the disadvantage of this, or what's the advantage of Unicode over ASCII? And the advantage is that Unicode can represent over 4 million characters, which is enough to represent every single letter in all of the languages across the globe, whereas ASCII can't do it. When you think about the number of different languages, so, Japanese, Chinese, all the different alphabets, Cyrillic, French, German, and you just run out of space. So hence Unicode allows you to represent every single character. That's pretty much all they can ask you there, okay? That is it. So that's your characters, easy peasy. And literally, if they ask you a question, they're going to be riffing off the fact it's a set of characters that the computer can understand. And I suppose the other thing, which is on the top here, which probably I should have put lower down, is this, which is that in a character set, whether it's ASCII or Unicode, each character, so A, B, C, D, A uppercase, A lowercase, spacebar, left arrow key, exclamation mark, every character that you need is represented by a binary number. So there's a table that's got A to Z capitals, A to Z small case, all the numbers, all of the special characters, shift, escape, blah, 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 all of those. And each of those has its own binary number. And it's a kind of, it's not a kind of table, it's in a table. And that is how ASCII works. Good. Okay, we have made quite exceptional progress. Right, let's go on to the next one, which is here. Okay, lastly, I think, so this is working out the size of a text file, because I'll come and talk about images and sound next time. But a text file, this is so wonderfully logical, and it couldn't really be anything else if you think about it. Working out the size of a text file, it's the bits per character. So let's go back to here. Bits per character, okay. 1 byte per character for ASCII, and 4 bytes per character for Unicode. So you'll need to know which character set it is. Yep. So 1 byte per character for for ASCII, sorry, and 4 bytes per character for Unicode. And then you do some simple maths. So you find out how many characters there are, and you work out how many bits per character, and you just do that simple bit of maths, okay? That is all that you have to do. I'm going, for the sake of just being helpful, to go back to here for you, Abra, which is just this, okay? So this is converting to hex. Converting to hex is really simple, but you've got to go through binary to hex. So if you're going from hex to denary, go to binary. Once you get to binary, you know what you're doing. It's those tables. When you go from denary to binary, it's the same thing. Go to binary and then convert it. So for example, this number 5F, if you're asked to convert this to denary, you write 2 nibble tables, 1, 2, 4, 8, and over here 1, 2, 4, 8. And you simply carry out the same operation. What's the biggest grid number that goes into 5? Well, it's 4. What's the leftover 1? There it is. So we've got a 1 and a 1 here. We then say, what is the biggest grid number that goes into F? You need to know that F's 15. So 8 is the biggest, and that leaves 7. 4 is the biggest number that goes into 7, so you do a 1 here. Your leftover, yep, 2 is the next biggest, 1 is the next biggest. And all you've got to do is smash those 2 tables together, so you end up with an 8-bit binary table. And then do your maths. 64 plus 16 plus 8 plus 4 plus 2 plus 1. Okay, and the answer was a magical 95. Okay, so that is your hexadecimal done and dusted. Binary shifts all sorted out. Let's do a little bit of a quiz and see how we do with this. Fingers on the buzzers, please. Apart from the fact you haven't got any buzzers, doing a logical shift left does what to a binary number? Answers in the comments, please. Oh, Dan's come in. Dan's come in with B, and Abra's come in with B as well. And Abra's asked me a good question, actually. And that is, the number you've given there, it won't be any bigger than that. It's quite easy. That's literally going to be it. They're not going to make you do more than that in hex. I'll double check that, but I don't think it's more than 2 digits. I'll have a look in the spec tonight, but I think that's as big as it gets. So we've got Dan, who said B. We've got Abra, who says B. We've got Warren, who says B. We've got Ben, who says, hi, Ben. We've got Lakshay, who says B. Hello, guys. So, yeah, you were all absolutely spot on. That was, let me get off my thing. You were all, go away. Yes, you are all absolutely spot on. The answer is B for multiply. What about this one? Doing a 2-bit left logical shift has what effect? Does it A, divide the number by 2, B, multiplies it by 2, C, divides the number by 4, or D, multiply the number by 4? Right to divide. It works for me. I don't know why. I can imagine a king saying that. It's my right to divide. So what do we think? 2-bit What happens with the 2-bit? I will be interested to see. Ooh, we've got lots of answers coming in. Hang on a minute. So I think, hang on, we've got Warrant who said D, we've got Dan who said D, we've got Ben who said D, we've got Abra who says D, we've got Om who's gone ... which is a good call, I reckon. We've got Lakshay who said D. Well, what this is clear is that you actually understand this. So well done. That is outstanding. Let's push on. What about this one? Which answer has correctly applied a 1-bit left logical shift, which is a heck of a mouthful, to 10001100? I'm not repeating the question. I will. Which answer has correctly applied a 1-bit left logical shift to 10001100? What do we think? Oh, we've got questions. Yeah, almost getting involved in his own way, but ... could have been right. Abra has said B. What do we think? Dan's gone for D. Oh, we've got a difference of opinion here. Anything else on this? Dan said D. Any other ideas? 23. That's very good. Good that people have shown up today, in spite of me being silent for the first 5 minutes. It may have been a blessing. B and D is the same. Oh, is it? B and D. Oh, well spotted. B and D is the right. God, dear me. Teachers, you can't trust them, can you? Let me give you the right answer then. But the answer is D. Or B, it turns out, because they are identical. So, Abra, you were right. Dan, you were right. And obviously, I got so excited I just wrote the same number out twice. It's such a good number. All right, let's try this one and see how we do. Convert the hex number C9 to binary. Are any of these the same? No, they are different, I think. Yes, they are. God. And you know what? That's really well spotted. Who said that? Because I've shown this 4 or 5 times. CCTV. Excellent. CCTV. We haven't got a T, though, have we? B and D is the same. Om says C. What do we think? Is Om on it? Convert the hexadecimal number C9. Okay. If I'm being lazy and working out in my head, we know what C is. A is 10, B is 11, C is 12. Okay. You can do some maths. 12 plus 9. Yeah. 21. And then work it out from there. What have we got? We've got Om who's saying C. Anyone else hazard a guess on this? Take you slightly longer to work out. Convert the hexadecimal number C9 to binary. It's just a process, isn't it? Okay, the method for this question would be that you would draw 2 nibble tables, right? So you would do one for C and you would do one for 9, okay? You need to know that C represents, if we've got 1 to 9, A is 10, B is 11, C is 12. So you'll do one nibble table, which is 1, 2, 4, 8. You do one for 12 and you do one for 9, right? And that would give you the binary number, and then you smash it together, yeah? I'll go through it next time. Ask me when I'm back in class. So it took a bit of time, that one. That one was tricky, wasn't it? So we've got Dan who's saying A. We've got Lakshay who's saying A. Let's see what the correct answer is. Okay, we've come with Warrant saying A as well. Let's have a look. The answer is indeed A. That is outstanding. Palak got it as well. Hi, Palak. Palak got it as well. All my star students nailing this, which is really good. It takes a bit of working out. That's as hard as it's going to get, though. Do remind me, Abra, in class. I will go through that with you, okay? Because the maths ain't hard. It's just the process, which is a bit weird. Okay, what about state the denary representation for the binary number 00111101? So you would drop that into an 8-bit binary table, 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, and then you would do the maths. Yep, that's what you got to do. Oh, Abra, you're not in my class. No, you're not in my class. Of course you're not. Shame. I will speak to... You've got Miss Green, haven't you? I'll speak to Miss Green, and she can go through it with you. But the maths-wise, it's easy peasy. And in fact, if you get a moment, Google... Oh, what's his name? There's a guy on YouTube who's really good at this. It'll come to me. Okay, we've got some answers. We've got Dan with B, we've got Lakshay with B, we've got Palak with B, we've got Warrant with B. Well, I find it impossible to believe that any of you would be wrong. which indeed you aren't. So congratulations. That is outstanding. Yeah, I'll have a think about that. Yeah. Right, forward. Let's go on. Let's do this one too. Okay, what letters does hexadecimal use? This is very easy. But obviously, if you don't know it, the whole thing becomes quite difficult. If you're going to use letters from A to Z, that could be problematic quite early on. 45, so we've done 45 minutes. Not much more to go. What have I got? I've only got another couple of questions, so we'll be done then. What do we think? What does it use? Okay, look at these coming in. We've got Abrai says B. We've got Lakshaya saying B. Palak saying C. We've got Ben saying C. Let's have a look and see how you're doing. The answer is, drum roll, it's C. Excellent. Okay. Convert 173 decimal or denary to binary. 173 decimal to binary. A bit of practice with these. Yeah, I knew you were just bluffing, so that's fine. So convert that decimal to binary. And again, how do you do this? You draw out your table, and you're going to have 1, 2, 4, 8, 16, 32, 64, 128. 128 is going to be the biggest number, so you'll stick a 1 in that far end box. You'll do some maths and work out what the modulus, the remainder, is from 128. It's going to be 2 to get to 30. It's going to be 40 to get to 70. And then it's 3, so you've got 45. Then you've got to go through the list and pick the next one out. What do we think the answer is here? It's probably worth having a practice of these because there's almost a grade boundary in this, especially if they go big on shifts. And again, I don't think there was a binary shift in the last paper. Not that you can necessarily predict, but they do often vary a bit. So Dan says B, Abra says B, and Warrant says B. Shall we see where you are? It is B. You are outstanding. That is wonderful. Let's go forward. I think we've got one more to do. Question 8. Convert the binary number 10101010 to hex. This one, yeah, Palak, you were absolutely... Hang on, let's do some more crediting people here. B, that was excellent. Abra, you got B, and Palak, you got B. You are all doing really well. Okay, so what do we think about this one? Convert the binary number 10101010 to hex. What is it? So think about how you might go about this. You're going to think about 2 nibble tables, 1010, 1010. How can you convert that to... Lakshaya's come in really quickly with C there. That is impressive. Quick maths. That's really impressive. So we've got C for that. 48. I don't want to keep you, so I'm going to push on. The answer is C. That was super quick, Palak. Well done. And that's it. So we are done, guys. We've covered. Yeah, Dan, you absolutely spot on. It is C. Well done. We've had 24 people in. That's really, really good. Revision ideas. Yeah, Warrant, you're spot on. It was C. Revision ideas. Let's have a look at these. Things to think about. Do a bit of practice with the conversions because they are dead easy. But also, my recommendation is do it both ways. Binary hex, hex binary, binary denary, etc. I recommend drawing out the tables. And if you do it inside your head, do it twice. Because it's so easy to make a mistake. Practice different conversions each time. Be confident in that why binary question, because it will be there. Because computers use circuit boards. Circuit boards only have 2 states, 1 and 0, on and off. And on and off is very easily represented by binary. It's got 2 states, true and false. 1 true, 0 false. Boom. Loads of marks. Learn the effect versus perform. So in the question, do they say perform a binary shift, which means do the maths, or learn the effect of it? So it's dividing by 4, and you will lose precision or accuracy, okay? Learn the fixed size of storage media. So I fancy they'll do something on what would be the right storage media for a file that is... they've got 550 files of 8 bytes. So you've got to do some, and then in megabytes. So you've got to convert it and then talk about which would be the suitable storage device or storage medium. So for example, a CD, which is 740 megabytes, a DVD, which is 5.6, Blu-ray 50, And then obviously the biggest one is tape, which is like 200 terabytes. It's huge. And then you've got solid state, which I think is about 2 or 4 terabytes. And then you've got magnetic hard drive, which is kind of bigger still. I don't know, 10, 20, 30 terabytes, so big. Okay, learn the steps of binary addition, revise those registers, and actually I'll give out the revision planner to all of you next time. Guys, it has been a massive pleasure. I'm going to do images, sound, and something else next time. But I will see you in exactly a week. Well done for being here. 24 we've had, which is excellent. Very, very good. That's almost a class full. So well done, guys. I hope that was useful to you. I will go and make the chapter headings. It won't be tonight because I feel so rough, but I'll make you the chapter headings and I'll put it there for you, and I'll send you the PDFs that go with this. Also, have a go at the flashcards that I've sent you and have a go at the quiz. And you should probably nail the quiz now because you're all experts. Guys, have an amazing week and I will see you all later. Bye-bye.